Hello everyone and welcome to this next lecture. I'm sorry it took so long to get it out, but being quarantined is hard work in itself, so it's not always so easy to get time to record. Today we're going to talk about asynchronous computation, which is a super important topic in computation, not just in functional programming, in everywhere really. And it turns out that one really convenient way of expressing asynchronous computations is in terms of continuation passings that we discussed last time. Now, if you thought that that was sort of tricky and hard, and I do agree that it sort of can be pretty mind-bending wrapping your head around all these continuations, and there's a lot of stuff going on all the time. But this is actually a simplification. This is a less general thing than the general computation passing. So this will be simpler, I promise. So, why are these things so important? Well, non-blocking communication and non-blocking I/O are two really important things that we need to do, because we might have long-running processes and we don't want to wait and, for example, lock up a UI so we want to fire off a computation and then pretty much forget about it and maybe wait for it to happen at a later moment when we actually need the result. It's also super important for concurrency and parallelism, which is just another aspect of non-blocking I/O communication. And you probably know from other languages things like promises, tasks. I don't know if you've ever encountered observables. They are not sort of really what we are going to talk about today, but they are kind of related. In a categorical sense, they are the duals of the asynchronous. So they are like the cousins of it. We're not going to talk about those observables. If you ever stumble upon an observable, you know that you've heard about them. So, no blocking I/O. That means that we want to do some I/O operation. That could be mutate a variable, that could be writing to disk, it could be communicating over a network, whatever it might be. But the non-blocking operation will return immediately. And that means that it cannot return a value, because returning a value would imply waiting for that value to appear. So that means that any non-blocking operation that you're going to perform is necessarily going to have to return unit, the singleton empty type. And that has that implication that your computation will have to somehow mutate state. Either it does so by doing some I/O, printing to the screen, communicating networks, writing disks, updating databases, something. Because if it doesn't, then it's completely useless. Then it's a no-op. It's just doing some pure computation and discarding the result. Not much point in doing that. Now, we have so far learned that mutating state is usually a bad idea. Of course, if we're going to do I/O, then we're going to have to do I/O. So there's nothing more to say about that. We should be careful, but we just do it. But if we actually want to have a mutable variable, then it turns out that there are ways that we can sort of get around this. In a way, fake not having mutable state in the system that we will look at in the next lecture. And that's a super powerful combination together with this async and mailbox processors. But just to have a quick look at what this is. So in the previous lecture, when we talked about continuation passing, we saw that we had a normal function f from a to b, and we replaced that with a function from f from a, and instead of returning b, it returns a higher order function which accepts the b and returns some type R. And then the whole thing returns that type R. Now async is just the same thing, except that now this general type R that we had to drag around is just unit. Everything is unit. So now we can define this async type as being a function from A to unit, a higher order sort of function which accepts a function from A to unit, and the whole thing returns unit. And now we can write this f function instead of writing it in the complicated manner up there. We can just say f is a value from A to this embellished higher order type async B, or this sort of fancy type of B. So that now it's basically just A to B. In the previous lecture we also looked at composition, and we had a function called thrice, which was just using continuation passing to call the same function 3 times. Now we're going to look at this in a slightly different way here. I have this example function called trio, which is really duo, but because of the continuations it's sort of trio. Hard to name things. Now trio is the same as thrice, except that it accepts 2 functions and it accepts a value which is a continuation itself, v. So v is a sort of a normal value, but in this async world. So it's an asynchronous value. F is a function which takes an a, which is the value contained inside of v, and produces an async of b, or this continuation of b. And g again takes the b and produces a c, or an async of c. So if you look at it from using this async type, it looks much nicer like this. Here it is. V is an async a, just a normal value. You don't have to care about the internals of it and that there are any kind of higher order functions involved and all these complications. V is a value of type async. F is a function from an a to an async of b, and g is a function from b to async of c. And then we sort of have this slightly complicated way of composing them. Now it turns out, as we realized last time, that this continuation passing thing is actually a monad, and that the continuation itself was a monad. So then of course async of this a thing is also a monad, and then we can define bind for it in exactly the same manner. The only difference from the previous lecture is that now I've replaced this prime r general return type with unit. And then you can see, if you look at the lower line there, the val bind is a function of v async a, which is just a sort of a value of this monadic value, and then it takes a function from a to async b and produces a async of b. And this is exactly the same as bind for lists, for example, where you had list a and f is a to list b and producing a list b. So this is the sort of shove shove operator. So this works exactly the same way, and we don't really have to care about the internals. It's good to know about, but we don't really have to. And that means that now you can define a computation expression like we did last time. We did with this computation expression, but now we have this async computation expression, which is in the standard F# library. But it's pretty much the same computation expression that we defined last time. And now we can do the thrice function. I should have done the trio function here. Now we can do the thrice function using async instead, and the only thing that has really changed is the keyword async. And f is an async function returning an x prime. We let bang it so we can get the value, and then we can use that value again and again. Now the thing is, the return bang will take a normal value and return it, no, it will take an async value and return it, which is the sort of f returns an async. But I said this whole thing has to return unit, and that's why there is an async ignore, which is a function which takes an async containing a value and just ignores it. And now, if this f here is a pure function that doesn't do anything except by a pure computation, this whole thing is just pointless. But f could be a function which would do some I/O, and then this async start will fire it up and return immediately, and at some point it will complete the computation. We'll see some examples of this later. Okay, so let's have a quick look at some simple examples of how to use async and do asynchronous computations. So the first example I have is a really kind of silly one, but it shows a very important thing about these asynchronous computations. So in this example, I define a function a, which takes a unit and returns a string wrapped inside an async computation, which we now know is just a continuation, really, a continuation returning unit in the end. So the way I do this is that I create a async block, async computation expression, and then I just return hello world. And this will take the string, wrap it inside an async computation, and return the whole thing. And now on the next line I can run it, a unit, and then I pipe it into async run synchronously. Now this is sort of a little bit weird, because run synchronously is a function which takes a async computation containing some value t, in our case this string hello world. It takes some extra parameters, timeout and cancellation token. Those are optional, and we're not going to talk about them because that goes like kind of deep into asynchronous programming, which is a fairly large topic in itself, and I actually think you even have separate courses for that in the university. So this run synchronously, it takes an async computation containing a value t, and it actually returns the t. So it's sort of cheating a little bit, but it does so synchronously, which is kind of defeating the whole purpose of having it asynchronous. So what's the point, you might think? Well, sometimes you might end up with an asynchronous value and you just want to extract the value out of it, and you don't care about the asynchronicity. You just want the value right there, right then, and then run synchronously is your friend. It's also very good for debugging synchronous things, because you can actually run the computation and get the value out and see what's going on. So that's a first very simple thing, but it sort of shows you how to take a value and wrap it inside an async. So let's look at another example. So now we're going to do a proper asynchronous computation and do it asynchronously. And the way we're going to do this is, of course, since a proper asynchronous computation can't return anything, any value, we need to somehow to update some state. And so that's why I define a mutable variable underscore x and set it to 0. I've called it underscore x just to make very sort of clear for myself that this variable is kind of special. It's mutable, and be careful with it. In the next lecture we will look at mailbox processor, where we can get rid of this mutable and instead use the mailbox processor to handle the mutable state for us quite nicely. So this function b, it takes an argument x, an integer, and it returns, and the whole thing is returning async unit. And you see that there it contains an async block, and then there's just this variable update, which is essentially a function called returning unit. I could have written this slightly differently, like so instead. this, and then return unit. That would have been the same thing. So now this variable update happens inside this asynchronous block, and that's important. Okay, so I can call this with B42, and instead of passing it into async run synchronously, I now pass it into async start. And async start takes a computation, which is just a async value containing unit, meaning this thing cannot return anything, and the optional cancellation token, and the whole thing returns unit. So, and this will start the computation in the thread pool. So it will probably fire up a new thread and run it somehow, and when it's finished, it has done what it updates the value, and it's done. We don't really have to know what the details of what's going on. The system runtime will take care of it, but we can just run it. So let's see how this looks like. Oops. So there we go. And now you see that when I run it down here, B42 into async start, and I print _x 4 times. And the first time it's 0, the second time it's 0, the third time it's 0, and only the fourth time it's 42. And this is because it will take some time for this thread to fire up and get started. And meanwhile, the async start has returned, it starts printing, and the async value hasn't been updated yet. So it prints it 0, 0, 0, 0. And this time it happened to take so long that I actually had time to print it 3 times before it suddenly became 42. So let's try to do it again. Just see. You see that this is completely non-deterministic. This time it happened 2 times. 2 zeros. Let's do it once more. And there we go. 3 42s. So you see, depending a little bit on the state of the machine, what's going on, how long things take, there's a delay. So things really happen asynchronously. Now, if you go into proper async programming, there are ways to await computations. So basically what you want to do is you start the computation, fire it off, it goes somewhere, you can keep on doing things, but then at some point you will need the value, and you will have to make sure that you have it. So then you can actually await the computation. But that's a different story. So let's do a different type of async computation. Another example. So here I've defined 2 functions. One is called minutes. It takes a value s. It should actually be ms because it's milliseconds. It takes a millisecond value and converts it to minutes, which will be a floating point value, and then it will just return that floating point value wrapped up as an asynchronous value, an asynchronous computation. Very similar to the string. And here you see that I'm actually doing the computation itself outside of this asynchronous block, because there's nothing asynchronous about it. There's no need to do it inside the async, and I only use this async to wrap it, which this is of course a bit contrived. There's no reason to have this thing return something asynchronous typically, unless it's because you need to communicate this value back to some web server or something in an asynchronous fashion. Okay, give me a second. Okay, so we're back. So that was the minutes function. So here's the other function, sleepy. And again, what Sleepy will do is it will take some value n, which is just an identifier, just so we can see what happens. And then it will generate a random number generator RND. It will generate a random number between 0 and 1, multiplied by 10,000 and convert it to an int. And then we'll call thread sleep with that number of milliseconds. So thread sleeps accepts milliseconds and sleeps a thread for that amount of time. Now all of this is still happening synchronously. But now I'm going to create an async block, and I want to print asynchronously print the ID I gave it, the n value, and then I want to convert the seconds or the milliseconds into minutes and return that as well. And that minute, of course, computation is happening also asynchronously. So now instead of just calling minutes, I can't just call minutes and get the milliseconds back or the minutes back. I get an async containing the minutes. So in order to extract that value, I need to use let bang and bind it to m, and then I have this normal value that I can use, and then I return print tuple n comma m. And the print function, of course, returns unit. So this is actually the whole thing is returning unit, which is needed for async start. So the effect of this computation is to print. It's not updating any variables or anything. It just prints. But that's an effect as well. So we get the output out. Right. So that's the thing. So this shows how to extract asynchronous values out of asynchronous computations inside of an async block. Now I could have a number of these let bang functions that I need to call before returning. And the important thing to note is that those will happen synchronously inside this block. So it will call the first function, it will wait for it will return, it will extract the value, it calls the next function and the next function and the next function, and just like normal code. There's nothing special about it. So inside of an async block, all the functions that we let bang bind thing with are just like normal functions. We can work with them like any function, like whatever normal function that we use, completely synchronously. But the whole block itself, this block here, the async block, that will then get run as a asynchronous computation, as a unit of computation. All right, so let's see how this works. I call sleepy with the 1. The 1 doesn't do anything. It's just an identifier, a thread identifier, or whatever we want to call it. And then I pass it into async start, which again just takes asynchronous computation of unit and produces unit. So let's see how this looks. There we go. And it's waiting, and it's waiting, and there we are. So it prints in the end 1 and 0.0837 something minutes of wait time or compute time. We can run it again. We don't need to do that. I can just run it again. I will see that we'll get some other. There we go. Now it's slept for slightly shorter time. I can say R4. It doesn't affect anything except the. We'll see. There we go. So finally, we're going to look at a parallel computation. I'm going to add it here. And in this example, I have used a special function. I could have done this in many different ways, but I just wanted to show you this function that you haven't seen before, list unfold. So the normal fold, which is also sort of usually used as a reduction, it takes a list argument and a starting value, and then it will go over the list and accumulate this folding function over that list. So it takes a list, and typically it produces something which is not a list, but maybe a single number or a string, or it could produce a list of lists or whatever it does. But it will take a list and operate on that to turn it into something else. Unfold is the exact opposite. It will take some starting value and apply this unfolding function to produce a list. So I could have used a for loop here, or I could have just created a list of 5 elements in this case, and then used map or iter on it. But now I chose to use list unfold to show it to you. So if we look at this list unfold, it takes a function which takes an argument n, which will be an integer, and then it says if n is greater than 0, then it will return some. So this is an optional value, right? So if it returns some, it will continue unfolding. If it returns none, it will stop unfolding. So it returns the sum and the tuple of calling sleepy, and then it will do n minus 1, so that we count down from 5. And when it hits 0, it returns none. So let's see what this produces. I will actually put this into a let L equals, just do it like this, so then we can see a little bit better what's going on. So this L value here that we produced with this unfold, it takes, it produces simply a list of async unit values. Since these are async unit, the whole list is just filled with these async unit values. But this sleepy function, remember, since this is asynchronous, it hasn't been run. It's just, these are computations waiting to be fulfilled. So now we can take those this list of async unit values and pass it into async parallel. And we can look at the signature of async parallel. So async parallel takes a sequence, in this case a list, of async values or async computations containing some value t, where t in our case is just unit. And it will turn it around, so that instead of having a sequence of async computations, it will produce a async computation of an array of t values. So in our case, it will produce, async parallel will take this list of async units and turn it into an async array of units. Now if you remember, async start, it just wants async unit, and now we have async array of unit, which is not the same thing, so somehow we need to discard the array of empty values, and that we can do with async ignore, which just takes a async of whatever and returns async unit. Okay, so let's have a look at what happens here. So what I want you to look at carefully is that since all these computations inside this async list of sleepy are happening in parallel, we don't really have any control over any ordering here. So when I hit go on this thing, it will fire up a number of threads and it will start executing, and they will all sleep for different amounts of time, so the result will come out in whatever order. I have no control over it, as you will see, since everything is asynchronous. So here we go. Let's see what happens. Oops. Here we go. So here are, okay, so that's right. So first we got the ID 4, which slept for a very short time. Then we got the number 3, which slept again for some time, and 1, 2, and 5. So you see they come out in completely garbled order, and you see they are not even coming on the same, on different lines, because sometimes the result from one prints before the new line has been printed on the previous one. So we can run it again if we like, but you'll see that we get the different result. Just run it again. There we go. See? Yeah. 5, 2, 3, 4, 1. We can run it again. Oh, there's another one, yeah. All right. So that shows you a little bit about how one can do parallel programming in F# using these async computations. Oops. All right. So that was that. That's all we have to say about async so far. In the next screencast, I'll try to finish it today. We'll look at mailbox processors and see how they can help us manage mutable state, in particular when dealing with asynchronous computations. They're generally useful for a lot of things, and we're going to see them more when we talk about the model view update model for doing reactive programming in the yet following screencast. All right, until then, bye bye.